Conceptualizing area via elementary strips. Now, before we dive into the new material, let's take a moment to reflect on what we have already covered. In our previous chapters, we explored the theoretical foundation of calculus, specifically learning that the definite integral is essentially the limit of a sum. You've seen how we can add up many small parts to approach a total value. In today's lesson, we are going to make a transition from that purely theoretical definition to a much more practical, geometric application. Instead of just looking at sums of numbers, we are going to use integration to find the actual area of a region bounded by a curve. As you know, when we deal with simple shapes like squares or circles, we have standard formulas ready to go. However, in the real world, we often encounter irregular shapes, curves that don't follow a simple pattern, which are not calculable using those standard formulas. That is exactly where the power of integration comes in. Over the next few slides, I will show you how we can break these complex, irregular shapes down into simple pieces to find their exact area. Welcome, everyone. Today, we are beginning a very important new topic, conceptualizing area via elementary strips. The core logic, approximation by rectangles. On this slide, we are looking at the core logic behind how we actually calculate area. To find the area under a curve, which we can represent as y equals f of x, we use a process called partitioning. Think about it this way. If you have a shape with a curvy top, you can't use a standard formula like you would for a square or a circle. So, instead, we break that area down into simpler pieces. We use thin, vertical rectangles. As you know from basic geometry, the area of a rectangle is simply length times width. At first, if our rectangles are quite wide, they won't fit the curve perfectly. There will be gaps or overlaps where the rectangle sticks out above or below the line. However, here is the key mathematical trick. We increase the number of rectangles and simultaneously decrease their width. As we make these rectangles thinner and thinner, those gaps begin to disappear. Ultimately, when the width of these rectangles approaches zero, meaning they become infinitely thin, the sum of all these tiny rectangular areas becomes exactly equal to the total area under the curve. Now that we've established that the definite integral is essentially a limit of a sum, let's move from that theoretical definition into a practical, geometric application. This brings us perfectly to our next slide, where we will zoom in to look at just one of these single, representative strips to see how we mathematically define its height and width. Breaking down the elementary strip. First, let's set the stage. Imagine we have a curve, which we call y equals f of x. This curve is bounded below by the x-axis, and on the sides by two vertical lines, one at x equals a and another at x equals b. To find the total area, we aren't going to look at the whole shape at once. Instead, we're going to focus our attention on a single, representative vertical strip sitting somewhere inside that region. To find the area of this tiny strip, we follow a three-step process. Step 1, determining the height. I want you to pick any arbitrary point, let's call it x, anywhere between our boundaries a and b. Now look at the distance from the x-axis straight up to the curve. That vertical distance is our height. Since the curve is defined by our function, the height is simply equal to the function value at that specific point, which we write as height equals y, which is the same as f of x. Step 2, determining the width. We want this strip to be incredibly, almost negligibly, thin. In calculus, we represent this infinitesimal width using the notation dx. Think of this as a width that is shrinking toward zero. Finally, step 3, calculating the elementary area. Since this strip is essentially a very thin rectangle, we use the standard formula for the area of a rectangle, height times width. If we denote this tiny bit of area as dA, then dA equals y times dx, and to make it ready for the integration process we will see in the next slide, we substitute our height from step 1, so we get dA equals f of x times dx. Now that we understand the general idea of approximating area with rectangles from the previous slide, let's zoom in and look at the anatomy of just one single piece. This is what we call breaking down the elementary strip. By defining this single elementary area, we have created the building block that we will eventually sum up to find the total area under the entire curve. From a single strip to total area. Now that we have understood how to define the area of just one single, tiny strip, let's take a step back and look at the bigger picture. Think about the entire region we are interested in, starting from our left boundary, x equals a, all the way to our right boundary, x equals b. The total area, which we will call A, isn't just one piece. It is the accumulation of every single one of those tiny strips we just discussed, joined together from start to finish. This brings us to the very heart of calculus, the concept of integration. When you see an integral sign, I want you to think of the word accumulation. Integration is essentially a mathematical tool that allows us to sum up an infinite number of these infinitesimal, or infinitely small, parts to find a whole. To put this into mathematical notation, we start by saying that the total area A is equal to the integral, from a to b, of dA here. dA represents that tiny bit of area from our previous slide. But since we know from our breakdown of the elementary strip that the height is y and the width is dx, we can substitute that in. This gives us the area A equals the integral, from a to b, of y dx. And finally, to make it ready for calculation, we replace y with our actual function. So, the most complete way to write this is, the total area A equals the integral, from a to b, of f of x dx. In the next slide, I'll give you a great real-world analogy to help you visualize exactly how this accumulation process works in practice. Real-world analogy, the digital scanner. Now, I know that thinking about infinitesimal strips and dx can feel a bit abstract and purely mathematical. So, to help you visualize what is actually happening during this process of accumulation, let's step away from the graph for a moment and look at a real-world analogy, a digital flatbed scanner. Think about how a scanner works when you place a photograph on it. The scanner doesn't capture the entire image all at once in a single flash. Instead, it moves a sensor across the page, capturing the image one tiny, thin vertical line at a time. First, the scanner reads a single vertical strip of the image. At that specific position, it records the height or the intensity of the color and ink present. Second, it moves just a tiny bit to the right and captures the next thin line, recording the color data for that specific spot. Finally, the scanner repeats this process across the entire width of the page, accumulating all those individual vertical lines, one after another, until it has enough data to reconstruct the complete, full image. This is exactly what we are doing with integration. Just as the scanner captures thin lines to build an image, we are using integration to sum up those infinitely thin vertical strips, which we called dA in the previous slide, to reconstruct and find the total area under the curve. This concept of accumulation is the heart of integration, and it sets us up perfectly to see how we can apply this to a concrete mathematical example in the next slide. Illustrative example, area under a linear curve. On this slide, our goal is to find the area under the linear curve, y equals 2x, starting from x equals 0 and ending at x equals 3. Let's follow our four-step process. First, step 1, identify the elementary strip. Remember what we discussed in the previous slides? We need to define the dimensions of one single, tiny rectangle. At any arbitrary point x, the height of our strip is determined by the function itself, so the height is y, which equals 2x. The width of this strip is that incredibly thin, infinitesimal change we've been calling dx. Moving to step 2, express the elementary area. Since the area of a rectangle is simply height times width, we multiply our height, 2x, by our width, dx. This gives us our differential area, dA, which equals 2x dx. Now for step 3, set up the integral with the limits. We need to tell the integral where to start and where to stop. Our region begins at the lower limit of x equals 0 and extends to the upper limit of x equals 3. So, we write the total area, A, as the integral from 0 to 3 of 2x dx. Finally, step 4, evaluate the integral. To do this, we find the antiderivative of 2x, which is x squared. We then apply the fundamental theorem of calculus by plugging in our upper limit and subtracting the value at our lower limit. That is 3 squared minus 0 squared. This simplifies to 9 minus 0, giving us a final area of 9 square units. Now here is a great way to check your work. If you look at this shape geometrically, the region under the line y equals 2x from 0 to 3 actually forms a right-angled triangle. The base is 3 units long, and since the height is 2 times 3, the height is 6 units. If we use the standard formula for the area of a triangle, which is 1/2 times base times height, we get 1/2 times 3 times 6, which equals 9. This perfectly matches our calculus result, confirming that our integration was correct. Now that we have understood the theory of how these tiny strips accumulate to form an area, let's put everything we've learned into practice with a concrete example. As we move to our final slide, we will summarize the key takeaways and look at some common pitfalls to avoid when setting up these integrals. Key takeaways. All right, let's bring everything we've discussed today together. As we approach the end of this lesson, I want you to focus on these key takeaways, as they form the foundation for all the area problems we will solve moving forward. First, let's revisit the concept of the elementary strip. Think back to our scanner analogy from earlier. This is simply that thin, vertical rectangle we used to approximate a tiny, tiny slice of the total area. Next, remember how we determine the dimensions of that strip. The height isn't just any number. It is represented by our function, y equals f of x. This means the height changes depending on where we are along the x-axis. The width, on the other hand, is represented by the infinitesimal change, which we write as dx. This represents a width so incredibly small that it is almost 0. When we multiply that height by that width, we get the elementary area, which we denote as dA in mathematical terms. This is the product of y and dx, or f of x times dx. Finally, the most important part, integration. Integration is the process of accumulation. It is the mathematical tool that allows us to sum up all those infinite, tiny strips, starting from our lower limit, a, and continuing all the way to our upper limit, b, to find the total exact area under the curve. Keep these definitions clear in your mind, because in our next slide, we'll look at some common pitfalls to avoid when applying these concepts to actual problems. Common mistakes. Now, before we wrap up our session, I want to touch on some common pitfalls that students often encounter when applying the concept of elementary strips to find area. Being aware of these will help you avoid unnecessary errors in your calculations. First, be careful not to confuse dx with a constant value. It is tempting to try and treat dx as just another number, but in calculus, you should view it as a notation that tells you we are integrating with respect to the variable x. It represents that infinitely thin width we discussed earlier, not a fixed number you can pull out of the integral. Second, watch your limits of integration. When you are setting up your integral, always double-check that your lower limit, a, and your upper limit, b, are the actual x-coordinates of your boundaries. If you accidentally use y-coordinates or incorrect boundaries, your entire accumulation process will be off. Finally, a very common mistake is ignoring the actual function. When you see the symbol y in your setup, remember that y is just a placeholder. Before you begin the integration process, you must substitute y with the actual expression of the function. F of x always ensure that your final integral is expressed in terms of a single variable, in this case, x, so that you can evaluate it correctly. If you keep these 3 points in mind, you'll be well on your way to mastering the application of integration to area.